Hello everyone, this is Shouvick Mondal from IIT Madras. My talk is on Hansie, Hybrid and Consensus Regression Test Prioritization. This is the outline of my presentation. I will first motivate the need for regression testing in general. This is followed by related work. The need for consensus, why we at all go for consensus instead of the traditional test case prioritization techniques. This is followed by measuring effectiveness of prioritization in terms of failure detection rate. Then I will give a brief overview of social choice theory and try to map that into test case prioritization. We'll review traditional and hybrid prioritizations and then the consensus prioritizations in our work. Then this is followed by identification of prioritization representatives due to the consensus, and there is a bidirectional mapping. Prioritization representatives can be captured using correlation windows, and then we will discuss experimental results and finally summarize. So the motivation for regression testing is because today we have updation of software and we are all occupied with software, be it mobile software, PC, tablet, web application software. So the common thing they have is that they're getting updated frequently, and the problem lies in testing for regressions due to the updates. The problem is basically in the functionality, whether it is preserved in the newer version of the code. So to test this, we use regression test cases. So test cases are input combinations with known input values and known output values according to the older version of the code. So the newer version of the code is tested for functionality. In this work, we test only for failures. That means we check if the test case passes or fails in the new version of the code. So one way to do this is to execute all the test cases, which is the traditional retest all approach. But this has some issues when we have strict time budgets, in which case we won't execute all the test cases. The way around is to do regression test selection, execute only those test cases that are affected by the changes. So the first step towards this is definitely identification of which part of the code has changed due to the updation from older version to newer version, and then selecting the test cases with the affected coverage. So coverage here in this work is basic block coverage, basic block granularity, and then we have regression test prioritization. So this is the crux of our work, where RTP is regression test selection powered by test execution in a statically determined order. So the statically determined order can be because of many different heuristics, and that can be cost, that can be coverage, and there are many different exhaustive list of techniques in the literature. So this is a typical scenario of regression test prioritization and also regression test selection. So on the left hand side, we have a source.c, a C program, and on the right hand side, we have its update, source view under C. So this update is mainly in the form of line 8. So first, let me say this function fn, which is on a case by case basis, returns a number. Input is an integer n, and if n is even, it returns n square, else it returns n plus 3 into n. This was according to the older version of the code. Now the change due to line 8 has resulted in returning n square to n plus 2. So what you observe in this situation is that if we go for coverage wise redundancy removal, there will be test cases which will cover this part of the code. But doing that once is not enough. One reason is like we have an example here like f of 2. So two test cases with inputs 2 and 4. So one is 2 here. So f of 2 in the older version will return 2 square, which is 4, and f of 2 in the newer version will return 2 plus 2, which is also 4. So there is no discrepancy observed here. So coverage wise, this is fine. But if we have another test case, uh, that is f of 4, that will surely detect the discrepancy, and as a result, the test case is said to have failed. So one way to prioritize would be knowing the input values, which are the input values that are more likely to reveal failures. So let us take this example with having 100 test cases in the original test suite. And for this, we have recorded the test coverage, the basic block coverage for all these 100 test cases in the older version of the code. And we also know their expected output. So expected output is according to the older version source.c. So now the new version has come in and we perform the diff and we check that these are the, so if block has got affected, the test cases that is to pass through the if block must be having even numbers. So T1 to T100 containing randomly generated integers in the range of 0 to 99. And these are the 5 test cases that only pass through this part of the code, the if block. These are even numbers. And this is our running example. This T1, T3, 4, 15, and 99 is our running example test suite, regression test suite for the rest of the presentation. Unless, of course, I mention explicitly if another example comes in. And all of the test cases here that bypass this condition to if the else part, these are all odd numbered integers. So a review of the related work says that in ICSE 2013, Zhang et al. Gave one strategy where there was a spectrum between the greedy additional and greedy total prioritization strategies. So the greedy additional strategy, it selects the test case which is having the highest effective block coverage. So I'm being regression test prioritization here, so I'm using the term effective block coverage. And then the next coverage is adjusted for the remaining test cases, and then the next remaining effective block coverage, the next highest is selected. So there is a feedback, and this is greedy. The total is the total greedy total technique is on the other hand prioritizes the test cases which has greater total effective block coverage. So the higher the effective block covered by the test case, higher is its priority. So what Zhang et al. Does is they have a tuning parameter P, which is probability of fault detection in a particular code element. So they initially start with a probability of 1 because they are not yet covered, and they iteratively cover the different parts of the code, and they decay the probability, and they decay the probability by covering the parts of the code, and this helps in traversing and also realizing different heuristics in between the spectrum of greedy additional on one hand and greedy total at the other end. Then there is a consensus-based approach for fault localization. I think this is the first consensus-based technique approach that is applied to regression testing, but it was on a fault localization. So fault localization is actually also a ranking problem where the suspicious code elements are ranked according to their probability of having fault in that place in the code. So they used different techniques and the state-of-the-art traditional techniques, and they compared with some consensus classical approaches. And the next work is predictive test prioritization by Chen et al. This was in FSC 2018, and this is a prediction model given a library of prioritizations where they would train the prediction model by 14 GitHub projects, and they have six prioritizations in their library of prioritization: greedy additional, greedy total, adaptive random, search based, cost only, and cost. And then there is cost cognizant greedy additional. So having this training, what they do is they feed in a new GitHub project, and the prediction model will tell that this is the best or optimal test case prioritization, for this project given the changes. So the need for consensus. So here we see that prioritized test execution for our example will be due to one heuristic one. We have T3, T1, T4, 19, and 15. So this prioritization says that we execute the test cases in this order. And the test cases highlighted in red are the failed test cases. Now note that we do not know a priori which test cases will fail. We just need to run them. So we need to have heuristic. That's why we call this heuristic. And second prioritization says that you execute test case in this way. Third one says you execute in this way. And then we want to have the consensus, which is the base for this work. So this consensus prioritization actually combines the rank of individual prioritizations and obtains this. And this is actually closer in terms of failure separation starting from the beginning. By this, I mean to say that the optimal prioritization here is having three failures starting from the beginning position at position 1, 2, and 3 consecutively. And the consensus is having the failure position vector at position 1, 2, and 4. All the others have higher positions. So if you take the Manhattan distance between any position vector and the optimal, the consensus will be closer. So this is the motivation for consensus, and that is that individual heuristics, traditional heuristics, may not always be optimal. And if we have consensus-based technique, this can be more fruitful. So how to measure how it is fruitful? It is done by the prioritization effectiveness. So this is a 2D plot, bar and line plot. The bar plots are for the different prioritizations P1, P2, P3. P star is the blue thick line and optimal is the red dashed line. So on x-axis we have the timeline positions. So by timeline position I mean to say the time axis, instance of time. So this is at position 1, 2, 3, 4. So this corresponds to this position 1, 2, 3, 4, and 5. So there are 5 positions for that. And on the y-axis we have the number of failures, and this is so for a given position, which is a position 3, we have 2 failures up to this position. So if we plot this, so we have the bar plots for this P1, P2, P3, green plots, and the line plots for the others. That is opt and P star. If we normalize these two axes and take the area under the curve, we see that the area under the blue curve is just two triangles away from the optimal, and all others have more voids in that. So in terms of area under the curve, the geometrical interpretation of the effectiveness consensus is better here for this example. So the greater the area under the curve, the better is the prioritization in terms of failure absorption rate. So here, because we have the failures. So not in this work, we will be dealing with failures only, because in the traditional setting, fault information ceases to exist. They only exist in the controlled regression testing. So if we have the fault knowledge, and there is no point in testing it again, because we have the fault knowledge, we mean there is a test case to fault mapping. So to be as realistic as possible, we have this design choice that we will be going for failures only. So now a brief description of social choice theory. In social choice theory, we have the rank aggregation problem. So in rank aggregation problem, we have n different ranked lists and of m items each. And we have to come up with a ranking, which is also a prioritized list. So the test case prioritization fits into this problem of social choice theory because the ranking is involved. And we want to find a ranking P star that is in agreement to the extent possible with each of the input rankings. So this agreement is in terms of permutation distance. That is the complementary of that agreement. So the job is to minimize this disagreement and maximize the agreement. So in the social choice literature, these individual rank lists are called voters. So they are mapped to individual test case prioritizations, and we assume that there are no ties. By no ties, I mean that no two test cases will have the same rank, although they may have the same priority, but that priority tie was broken by some heuristic, maybe some randomized technique, which the traditional test case prioritizations in the literature currently do. And then there are M candidates. So M candidates are corresponding to individual test cases. So N voters and M candidates are the two parameters here. So to formulate the consensus test case prioritization, given a permutation distance metric, D, Pi, Pj are the two different permutations, and prioritize permutations P1 to Pn as input. Find an optimal permutation P star such that P is an permutation which minimizes the sum total of the disagreements in terms of Kendall-Tau distance, Kendall-Tau rank distance of this P, and with each of the individual input permutations. So Kendall-Tau distance is basically the number of inversions in one list with respect to the other. So there are two different ways to do this rank aggregation. One is being priority aware and one is by doing priority blind aggregation. So we'll see what priority aware aggregation is. So by priority aware, I mean the priority score per test case due to individual prioritizations, the inputs are known in advance. So in this case, we have the priority scores, not the ranks, priority scores due to individual heuristics. And what we want to come up with is a hybridized score, hybridized priority score due to the aggregation for each test case in the new ranking that I want to create. So here we want to deal with one heuristic, that is relevance confinement, which was designed by us in our earlier JSS paper, JSS 2019. And the model of hybridization is weighted sum hybridization. So I will briefly describe what relevance confinement is. So relevance is actually greedy total, and confinedness is actually the uh, test case. A test case is said to be confined to the changes if it covers unaffected code portions, unaffected basic blocks in our case, as least as possible. So by this, we have this denominator as cof t minus delta. So delta is the affected basic block, set of affected basic blocks, and cof t is the coverage of test case t. So the relcon of t alpha is the weight, alpha into relevance plus 1 minus alpha into confinedness. So relevance is actually the coverage intersection delta. So the number of affected blocks covered by the test case by the total number of affected blocks for the normalization. And this is anyway 1 by denominator. So the denominator says that the set of blocks covered by the test case minus the set of affected blocks. So the unwanted basic blocks should be as least as possible. So this is by being confined to the changes only. So the most confined test case is one which only covers the affected blocks. So relevance is given much more importance, and the primary weightage is based on the relevance, because relevance is a prerequisite for test case to be selected even before prioritization. So the test case has to be selected to prioritize. This is because the test case the intersection must be non-null, and the test case must execute at least one affected basic block. And, and this does not depend on the confinedness. And these are actually heuristically independent. So we have used the plus operator for the hybridization and the combination. And then there is a second one, that is priority blind aggregation. By priority blind is that we mean that we do not have the priority scores known in advance. What we know is like this kind of thing. What we know is just this ranking, that the test case is appearing in this order. We just know the permutation. How the permutation is created, what is the underlying criteria for that permutation sequence, we do not know. That way we are blind. So we have a standalone library of 13 different prioritizations. The example just I showed was there were 3 different prioritizations. So we had a standalone library of 13 individual prioritizations, and we build a consensus library of 6 consensus approaches. One is Kemenian consensus, the other is border count consensus, and then there are other 4 which are actually initial consensus approximations due to arithmetic mean aggregation, geometric mean, harmonic mean, and median aggregation. So by aggregation, I mean the initial approximation of a consensus for each test case is the arithmetic mean of the ranks of that test case in each of the individual 13 individual penetrations. This is the rank of the test case. So for geometric mean, it would be the geometric mean of 13 different numbers. So these 13 different numbers in this case will be the ranks of that particular test case in these 13 different individual approaches. The final penetration schedule. Those are combined and aggregated, and that way we only perform the initial consensus approximation for this AM, GM, HM, and MED. And the Kemenian consensus does it even further. So it does was the what the last point says, that is the initial approximation plus further it does refine the consensus to get rid of the uh, ambiguities. So actually there will be multiple different consensuses because of the ties and ties in the consensus, and there will be paradoxes and ambiguities. So there will be non-uniqueness of the consensus. So Kemenian consensus tries to figure out the strict sequential ordering, a total order to the extent possible by breaking ties. And it does it by the well-defined Condorcet principle. So the Condorcet principle says that if due to a profile of prioritizations, if so the test case that has to be as a first position in the consensus is the one that wins by a majority of votes by head-to-head comparison with other candidates, that means other test cases. And this is defined recursively. So the recursion is going for the extension of the Condorcet principle. The extension of the Condorcet principle is basically based on a type of quick sort. So in quick sort, we have a pivot, and on the left side of the pivot, we have the elements less than that values, and on the right side, we have the higher elements. So in this consensus-based mapping, we have left side of the consensus and right side of the consensus, and every element in the left side of the consensus is more preferred than that of the right hand side, and the right hand side is just the reverse. And this is just recursively defined and the divide and conquer rule. And every Condorcet alternative, the test case is finding its position, just like the thing that is happening in quicksort. So this is the Condorcet method. Boda count is a defeated aggregated strength. So for each test case, what Boda count does is it calculates how many in the profile of prioritizations. Let's say for the 13 prioritizations, test case TI board account is to be calculated, and what we do is we for each test case and for each prioritization and test case TI, we calculate the number of test cases that are behind it in the prioritization. That means the number of test cases it dominates for each individual approach, and that is aggregated for each test case and sorted. So this Boda count and the last four are non-Condorcet approaches. Let's go to the traditional standalone prioritization library. So these are the three. The first two has already been discussed. So the third one is the cost only prioritization, used also by Chen et al. In FSC 18. And this is shortest execution time first, cost only prioritization. The next is greedy additional, which is state of the art. And then there is the hybridization of railgun. So this railgun is the relevance confineness, short form is railgun, and we do it by alpha weightage. So alpha is 10% to 100% in increment of 10%. So this relevance score of 0, that is the relevance 0% relevance will give us the confineness, and 100% relevance will give us the relevance this way. So these are the 13 different standalone prioritizations, and consensus techniques will actually uh, accept this accept the prioritizations, the input sequence or due to these prioritizations, individual prioritizations. So this is the algorithm for hybridization. Initialize the consensus, and then for each test case, hybridize the score due to different heuristics. So heuristic H1 to Hk, this is a generalized hybridization function. So for the test case T, score of H1T and dot score of HKT. And then there is hybridization, and this is assigned to the score of the test case T in P star. And then we sort the test cases based on this hybrid score. And then we return it. So the time complexity is this. We need to take a look at this HIC. This term is actually the for each of the individual heuristics, the complexity of the heuristic. The cost of each heuristic is HIC, and since there are k, there is sum total of that. And then after this operation, we need hybridization, which is FC, cost of the hybridization function, and then the final sorting due to n log n. Now we illustrate the hybridized relevance confinement example. So this is one relevance confinement example where we have the isolated relevance confinement. So this actually looks like an adjacency list. So this is the test case. We have 10 test cases, and this is the basic block coverage for each test case. So like test case 1 covers basic blocks B1, B2, B3, B4, and B7. And the red highlighted basic blocks are the affected basic blocks. And on the right hand side, we have the numbers in parentheses as the relevance code. Note in particular, this test case is highlighted in blue in the sequence, Faraday sequence. These will be our test cases of interest. The confinedness heuristic says that the test cases should be executed in this order because of its confinedness up to the changes. And if we combine them, we have this. So here we have 3, 10, 1, and 2. Now, this Relcan unweighted is equivalent to 50-50 weightage and is also equal to just assigning no weights to anybody. Now, how about hybridizing 80% relevance with 20% confinedness? So we first need to see what relevance confinedness. So what Relcan in short, that is the unweighted version says. It says that 3, 10, 1, and 2 are the first 4 preferred test cases. And relevance only alone says that test case 1 should be the penultimate position. So if we just combine them, what it will do is 80% weightage to relevance will bring test case 1, test case 10 down. So here it has happened that 3, 10, 1, 2, they are still in the first 4 position, but because we have given 80% weightage to relevance, and relevance alone says that it should be at the 9th position. So this 10 is pulled down after 1, 2, 3. Now for 80% confinedness and 20% relevance, so we'll see the confinedness says that P2 test case should be at the last. So it brings this T2 from the 4th position to the last position in the Relcan hybridization. And see that there is a gain of 1 test case position. This is because there is still 20% weightage to relevance. So we can see that assigning different weights to the relevance score, the different alpha values will give us actually a spectrum of prioritization within the relevance confinedness and different schedules. And we can observe different failure detection effectiveness. So now we come to the consensus prioritizations. So we revisit the example, and like I said, there will be no unique consensus in some cases. But we'll see how this happens. So first we'll discuss the goal of any consensus operator. So the goal of any consensus operator is to maximize the agreement and equivalently minimize the disagreement. So the D for the disagreement is the distance function. So distance function is typically the Kendall-Dow distance and also called the Kemeny-Kendall distance. The maximization of the ranking agreement score of the consensus is based on a graph model. We'll discuss that in a short while. And minimization is minimization of the sum total of the inversions. And this is also called Kemeny score of P star of the final P star with each of the individual inputs. So the consensus by Kemeny-Young method. This is a classical approach from social choice theory. The general approach says that the voters are allowed to give preference such that they have the liberty to not select all the test cases, that is not giving preference fully. They can give partial preferences also. By this we mean that if there are 10 candidates and they can just give the preference for 5 candidates and just leave the rest. And they also allow the traditional approach, they also allow ties in the rankings. However, for in this work, we have two assumptions. One is no ties present in the input prioritizations, and we assume explicitly that the price ties have been resolved due to the heuristics in the test case prioritizations, and all heuristics prioritize all test cases. So if there are n test cases, if there are n test cases and k heuristics, so each of these k heuristic will prioritize. That means they will return n permutation. So if there are n test cases. So the original formulation is NP hard for even 4 voters. So 4 voters corresponding to different, so corresponds here to different prioritizations. So there is a workaround. The workaround is due to a quick heuristic that uses randomization. So we'll see what this is. The first step is to calculate an approximate consensus. So the approximate consensus is by the arithmetic mean of ranks per test case across all input prioritizations. So this is just what I said in the beginning, like arithmetic mean, geometric mean, harmonic mean, and median. We all perform this first step. Board account does a different thing, but K-many consensus has further steps. Let's look at what the steps are. After this initial approximate consensus, it has n independent iterations, and in n independent iterations, it tries to refine the initial consensus independently using a shuffling window of size m. So it shuffles window of subsequence m, subsequent size m, and reevaluates the ranking score. So the ranking score, the higher the ranking score, the better. So the ranking score is also called the agreement score, and this process goes on for each individual independent iteration until it is no longer possible to increase the agreement score. And at this point, there will be many orderings that give the best score. These are the optimal orderings, optimal iterations. So there will be ties. So to alleviate this issue, what it will do is it will just create a final arithmetic mean of the ranks once again, but this time only for the orderings that give the best score. And in the final step, the final ranking will be returned. But the time complexity will still this workaround is still order of n cross 2 power m. So n is typically in the range of 0 to 200. So that means 200 iterations are there, and shuffling window is of size 1 to m. So this window is actually exhaustively trying out the 7 permutations and combinations. So this is still costly. So to illustrate the KY consensus, we have the profile of prioritizations. We have two different prioritizations which rank the test cases in this order. The first one says execute test cases in 15, 3, 1, 19, and 4, and this is the other one. Kemenian consensus says that there are 6 optimal consensus approaches, 6 optimal consensus orderings with the same agreement score and the same disagreement score. These are the 6 different orderings. So we'll see how this agreement score has happened, the calculation of the agreement score, how this has happened. But before that, we need to discuss what a preference graph is. So the preference graph is the heart of any social choice theoretic consensus, be it prioritization, be it in a ranking problem. So this is the preference graph for our profile R. So this preference graph we have as nodes the different test cases, and there is an edge between T1 to T4 if there is a preference. If test case T1 is preferred to T4, T1 to T4, and the weight is 2. The weight means that how many of the voters prefer it that way. So T1 to T4, 2 voters prefer it that way. So T1 should be executed before T4. This is said by P1 and also this is said by P2. So likewise, the others are calculated, and this is a directed graph, directed graph, cyclic graph with non-negative edge weights. Now, from this, we can calculate the agreement score of 115.9934, this one, the highlighted one, and we see that this agreement score for this sequence will be obtained from this preference graph, the edge weights. So mod of T1 arrow T15 is the edge weight of T1 to T15. So T1 to T15 we have edge weight 1. So the summands are these different values, these different edges. So why only these edges? Because for this sequence to happen, we need to have T1 at the beginning. So T1 should be before T15. So T1 should be preferred to T15. T1 should be preferred to 99. T1 should be preferred to T3. T1 should be preferred to T4 simultaneously for T1 to appear at the beginning. And then T15 as the second one. So and this happens all the way, and this calculation gives rise to this score of 16. Now we want to find the majority graph. So because we want to find the Condorcet alternatives. So here we have T1, T4. So these are all Condorcet alternatives. So the Condorcet winner is T1 because it is the most preferred. Then the Condorcet loser is T4. Now how the others, how the Condorcet alternatives find these positions is based on the calculation involving a majority graph. So majority graph is obtained from the preference graph. First, let us focus on the blue edges and the vertices. So the blue edges correspond to the strict majority graph. So by strict majority, I mean to say that there is an edge in this direction T1 to T4 in the strict majority graph. If the weight of T1 to T4, if the edge weight of T1 to T4 is greater than the edge weight of T4 to T1. So here in the preference graph, we see that T1 to T4 is 2. So 2 minus 0, 2 is in this direction because the majority prefers is this way. So because there is no edge in the other side, because the majority, and this will be, and this strict majority graph will be, in general, the majority graph will have non-negative weights because it is the majority, what the majority is preferring. Now, in the strict majority graph, we have the strict restriction that T1 arrow T4, the edge weight of T1 arrow T4 to exist, the weight of, that is the mod of T1 arrow T4 should be greater than mod of T4 arrow T1. So this is now relaxed in the weak majority graph where the greater than is changed to greater than or equal to. So now as soon as we incorporate the equal to, we see that this 1 and 1, they have come in, and these red dashed edges corresponding to the weak majority graph. So the weak majority graph is actually a super graph of the strict majority graph. And this majority graph is a prerequisite for the determination of cycles, non-uniqueness of the consensus, multiple optima. So we'll see how that happens. So we see that if there are cycles in the weak majority graph, so the weak majority graph is the total one. If there is any total on the right hand side, including the privileges. So if there is any cycle in the weak majority graph, then there will be ties in the initial consensus approximation, and also ties in finding ranks of the Condorcet alternatives, and also in the consensus template. I will come to what template is. So here we have T1 to T15. They are, we can see that they are one reachable from each other, and there is a cycle of weight 0. Now these edges with 0 weights, they might seem prima facie useless, but they have a different important connection to whether there will be ties in the rankings, there is any unique Condorcet winner or not, there are at all unique consensuses or not, whether there is any optimal sequence that will give the highest agreement score. So all this will come into play depending on whether there are cycles in the WNG, the weak majority graph. So to find the consensus, what you do is we perform reduction of this majority graph. So we begin by, so we begin stage wise. So in stage 1, we find which one is the Condorcet winner. So the Condorcet winner is defined by looking at the graph where the in degree is 0. So here the in degree, I mean in the strict majority graph, I am talking about the strict majority graph for now. In the strict majority graph, the vertex that has the in degree of 0 is the Condorcet winner. So here we have in degree of 0 for two vertices, and also they are reachable via uh, reachable via edge of length 1 in the weak majority graph. So because there is any cycle, and there is, so cycle leads to kind of paradox, like there is ambiguity in which order to prefer. So because we have T1 and T15 tied, T1 and T15 will appear tied for the first rank. So there is no unique Condorcet alternative here. So the Condorcet loser is T4 because it is having a degree of n minus 1. So n is 5 here. So it is the least preferred test case, and majority prefers it that way. So the next stage is to find the positions for the test case 3 and 99. So in the stage 2 begins by removing all the vertices and edges that have happened so far, found their positions. So we are left with T3 and T99, and we see that they are not reachable. They got disconnected in the strict majority graph. Of course, they got disconnected, and then there is a tie. So this actually is a consensus template. So by template, I mean it is a representative. So this representative can, so there are multiple consensuses. So there are actually 2 into 2 into 1, 4 different consensuses that can result from this one, and they will all have the same agreement score. So this is a representative, a template, because it simultaneously captures all of the multiple optimal consensuses. So we need to map these prioritization representatives. We need to capture these ties using parallelized windows, because we don't want to violate the preference of anybody. In traditional scenario, what would happen is that generally a strict ordering, so this is a partial ordering, so generally a strict ordering will be enforced to arrive at a consensus. But for the test case prioritization, what we do is we want to respect the priority due to individual heuristics to the extent possible, and even going beyond that. And the beyond comes here in terms of going for ties. So here the ties, so if this can be translated in terms of prioritization, is that there are three different positions, position 1, 2, and 3. Test case 1 and 15 should be parallelly executed at position 1, so that both P1 and P2 are given preference simultaneously. So they are favored, their opinion is also favored simultaneously. T3 and T99 would be executed at position 2 and T4 at position 1. So there we need to have two-threaded and one-threaded configuration. So this two-threaded configuration, I mean by this I mean to say one parallelization window of two threads, parallelization window of two threads, and the sequential execution. So the window configuration for this will be 2, 2, 1. So we'll see that. So we have this example, and the profile of prioritization, we have this P1 and P2, and the template that gives that arises because of the majority graph is this one. And this indeed satisfies 4 out of 6 K-meaning optimal consensus, just like I discussed. They will have the same agreement score. For the graph that I displayed, they will have these 4 things, and these are the different things that will happen because of other calculations. K-meaning will find them. And the initial approximate consensus by AM, GM, HM, and median, they also give a prioritization sequence of the consensus that is also satisfied by this template. So we can see that this template satisfies many such consensus prioritizations at the same time. So this makes sense to execute this template, this representative, using parallelization windows. Of course, uh, assuming that all test cases are independent and they can be executed in parallel. So the border count also comes in here and says that the prioritization, consensus prioritization order due to border also is satisfied by this template. Although it is not, although the border is not a condensate principle, even though we can say that the K-many is a condensate principle and the others are non-condensate principles, it doesn't matter. So we can just satisfy this template and we'll now focus only on this template, how to execute this template. So we have this template. The one way will be to form a total order from this partial order. So that is sequentializing them. So just treat it of this in sequence like 1, 15, 3, 99, 4. And these are the execution units. So sequential order is just a total order. And we have execution units E. And this is executing sequentially. Blue parts, and so the blue positions means the test case passes and the red ones mean the test case has failed. So in terms of failure position vector along the execution timeline, so is timeline is increasing towards the right from left to right. So in position 2, 3, and 5, we have the failures. Note, however, that the optimal failure position should be 1, 2, 3. So although this is a fictitious prioritization, the optimal one. So the respecting window configuration, just like I said, 2, 2, 1. This says that there are windows failing at all positions. So here, the thing that is to be carefully noted is that the window is considered failed if at least one test case fails. Now, the reason for this design decision, is that we don't know a priori which test case will fail. So, in a parallel window, different sequential positions are mapped to one parallel position. So, in the sequential setting, we had 5 positions. Here, we had 3 positions. So, parallel position 1, parallel position 2, parallel position 3. So, the test case has failed. That means the window has failed in position 1. Window has failed in position 2. Window has failed in position 3. So, this is actually the optimal scenario if we go for the windowed configuration, windowed execution. Now, this is a little bit less, and in general arbitrary lists with different tie sizes will be allocated different window sizes depending on the size of the tie. So we'll see that an example later. So here we don't have much parallelism, we have only 2 maximum. How about increasing the parallelism to 3? So depending on the hardware availability, we have 3 execution units and we execute them in window size 3. So note, however, that here the window size was non-uniform, 2 to 1, and it can be non-uniform depending on the size of the ties, because that will be non-uniform as well. So here what we have is having uniform size of 3, and here we have uniform size of 5. So here in all cases we have this window as the window failures at the optimal positions, and of course these uh, green green dashed in thick edges. This is the best way to deal with the prioritization, respecting this representative, because the others are all done so by first enforcing a strict sequential order. So in the first case, we anyway have the strict sequential order, and here what you need to do a priori is first obtain the sequential order, then chunk the ordering in window sizes of 3, and then execute. So this is the best way to go by, respecting the window configuration according to the die size. So measuring the effectiveness of prioritization, we had one metric EPS and EPS omega. So EPS is sequential, EPS omega is boosting EPS using windows, parallelization windows. And this metric measures similarity of the prioritization, the failure observation positions as a position vector with respect to the optimal position vector. So the optimal prioritization will give positions 1, 2, 3 if there are 3 failures, and it rewards a timeline of test execution with early failure observation. And so more, so a dense failure observation, compact failure observation towards the beginning of the timeline in the prioritized order will be given much more higher award. And in this work, we do the epsilon latency. So this is actually the end-to-end execution timeline latency when parallelization windows are involved. So because we have parallelization windows, the windows themselves inside are there is parallelism, but the windows across windows, windows themselves are in sequence. So this metric captures whether there is a load balance inside the window, because this can be possible by monopolizing test case. So there might be many parallel processes inside a window, many test cases executing due to different processes inside a window, and all of them are of different execution times. So the end-to-end window time will be dominated by the highest running test case, the highest longest running test case. So that is monopolizing that window. So this metric is based on this formula. So where we have n windows and we have cost of each window as Ci, C1 to Cn, and this weighted sum is by diminishing log weighted. So the log values decrease. So here it is n plus 1, then and followed by 2 at the last. So we did not go for 1 because 1 will just vanish this cost of the last window. This will not be captured here. And this is the Cmax is the cost of the heaviest window, and this is just the numerator, the log weighted, just this numerator replacing each Ci by the Cmax. So this is the normalization, and 1 minus normalization gives us the value. The closer the value is to 1, the better is the load balancing. So it prioritizes. So this metric, the first metric, this is also normalized and says that the test case, the timeline that leads to early failure observation is much more fruitful. This is with respect to the failure observability. The second metric doesn't depend on the failure, and it says that whether the prioritization is effective. So it says that and the windows that are very light, they don't have that much load imbalance inside, and that have they are light and lightly loaded windows. They are quick, short running windows, and they occur early in the timeline, prioritized sequence, prioritized with combination of parallelization. That is given much more weightage. So the highest weightage is given to the first window. So and then there is a decrement, diminishing log weightage. So a window that appears, so a heavy window, if it appears early in the timeline, so that just worsens things. So we won't mind if a window, a highly loaded window appears at the last. So actually, this says that we want one window we executed early, and that has to be the window with lightly loaded, light workload. So this actually captures whether the parallelization is effective or not in terms of end-to-end load factors, whether the load imbalance comes into play. If we increase the window size, and different window size, different window configurations will give us different values. So we'll see that. So first, let's revisit this example. So here we have EPS value. So EPS was optimal because EPS measured the optimal prioritization and similarity with optimal prioritization. This is actually the optimal prioritization. So they have the EPS values with validation windows will be 1. Here we don't have that because this is not the optimal position. Optimal position will be 1, 2, 3. Here it is 2, 3, and 5. So here it is optimal position. Position here is parallel position, the position of the window. We see that there are load imbalances even if we have the same EPS value. So here we have two different configurations for the same prioritization. So here the prioritization is of a permutation of 10 test cases: 1, 3, 5, 2, 8, 7, 4, 9, 10, and 6. And they all have these windows failing at the parallel position, each of the parallel positions. So here there are 3 positions. First position, test case, and the window has failed. Second and third also failed. This also happens here. But the first case has the window configuration 5, 2, 3. So this might be due to the dice, and the cost of this window, first window, is 3. So 3 is the cost for test case T5. So you can see that this monopolizes the whole window, and cost of this window is 3. So likewise, these are the results for the others. And we see that the EPS value is 1 for both these. But the window configuration 533, 523, and this is non-uniform windows, and this is uniform windows with a possible fragmentation at the last position. We see that different configurations they indeed give us different load balances. So so this EPL has just shoot up from 0.261 to 0.346. So this 3331 gives us a better correlation in terms of load balance. So this is the EPL metric. Now let's move on to the experimental results. So we had this experimental results. We had this machine, 40-threaded machine running Linux kernel 3.10. We used LLVM for the normalization of the source code so that multiple front ends are supported. We built the framework Hansie using G++ 5.3.1 using the F1MP parallelization, and we had 20 GitHub projects, 20 benchmarks from SAR and GitHub. So these are the interesting research questions that we targeted. So the first one is, what is the impact of relevance weight on hybridization? So this came around 90% relevance gave us the best result for hybridization. The second one is traditional versus consensus effectiveness, whether at all consensus is effective in the first place when we compare it with the traditional ones. So I will discuss only the highlighted components of the RQs, and for the rest I will just give one or two sentences. For comparison with state of the art, so does it make sense to do the consensus prioritization, and how does it fare with the state of the art? So for state of the art, we chose adaptive random testing, prioritization, greedy additional and greedy total. So we found that we were able to beat them on some occasions, and the other way around, they were able to beat us on some, because we could not, consensus could not beat them in all occasions, because they are actually fine-tuned and tailored for prioritization algorithms. Social choice theory per se is actually different, targeted for the rank aggregation problem in a general sense. This is actually voting. So I wanted to bring it into this, map it into this regression test prioritization problem and see how it goes. So then there is execution parallelization as RQ4. What are the effects of parallelization windows on consensus test case orderings? So answering RQ2, we found that consensus outperformed individual prioritizations, and harmonic mean consensus prioritization by harmonic mean of ranks was the most effective one. So this 55.22% was the number of occasions when the consensus used to outperform the individual participating heuristics. By this I mean to say that there were 260 occasions total, because there were 20 benchmarks and 13 individual heuristics. So for each individual heuristic, we calculated the effectiveness score, and then each of these uh, consensus technique performed the consensus on the result of the 13, that is the prioritization of the 13 different heuristics, and then again calculated the confinement, again calculated the effectiveness score for the consensus. And we found that in HM was able to beat the individual approaches on 55.2% of occasions. This is actually the overall value. And the second best was the geometric mean. So this is the full table. So we had three different metrics: APFD, cost cognizant APFD, and EPS. So we see that consensus by harmonic mean was the best. The Boda and Kemeny, even if they were the classical approaches from social choice theory, they were costly and they were less effective in terms of effectiveness of failure observation. So we can see that using just simple techniques, a quick approximation, we can tame the problem. And this is the ranking in terms of effectiveness, consensus effectiveness, harmonic mean, geometric mean, arithmetic mean, Borda consensus, median consensus, and Kemenian consensus. So the parallelization effectiveness, we saw that when we increase the window sizes in terms of 10, so from 10 to 20 to 30, there was 8.56x parallelism speed up. And this was because there were overhead of processes, things were not embarrassingly parallel, and there were load imbalances, just as we saw in the PL omega calculuses. And EPS values, the sequential started off well, and when we increased the parallelism, we saw non-decreasing trend with an increase in the parallelization factor. So this is the parallelization factor RESP. So this is the RESP is the window configuration according to the tie size. So we found that overall in all our experiments, the maximum tie size was 4. So, and it increased in this way, increasing 10, 20, 30 EPS values boosted further. So parallelization actually helped in having a better failure observation rate. Now this maximum tie size of 4 also says that 13 individual prioritizations were strong enough to combat paradoxical consensuses. So this paradox will be like an example of paradox will be the number of people preferring a certain test case to be executed before the other is equal to the number of people uh, dispreferring it. The major challenges to this effectiveness calculation for EPL, which is the overhead of isolated parallel processes and the load imbalance of the workloads. So to summarize, we discussed the first framework for hybrid and consensus regression test case prioritization. Showed that parallelization was indeed able to combat the non-uniqueness of optimal consensus and gave us um, boosted values of observed effectiveness in terms of failure detection rate and also different uh, informed ordering of the informed allocation of the test case window size. Window size will give us actually good imbalance, good balancing. We formulated a metric EPL. We did not discuss that in detail, but that was enough to quantify the end-to-end latency of test execution with parallel windows. So thank you. Thanks for attending my talk. You can check out the artifacts for these experiments at the Zenodo, and you can visit my webpage and can send an email to me at the following email address. Thanks.